All right, here we are, part 3, and we're going to look at an example of a very classic problem in physics called the inclined plane. So let me teach you how to do those. What we're going to learn today is we're going to put a box or object on an inclined plane, and it's going to go down the plane, and we're going to be able to calculate the acceleration down the
Can
plane.
we not do a shoe?
What's that?
Can we not do a
Let's
shoe?
not do it.
Look at Brian's shoe.
And the table.
Yeah, we're not doing the table. I don't know about the shoe, but definitely not the table. All right. Let me see if I can get this. If you would take notes on the space there, and we're going to work the theory through, and in the end we'll have a basically a simplified picture of the theory, which will be our working model. So, inclined plane, here we come.
Oh, I see what you did there.
Here is my inclined plane. One thing you need to notice about an inclined plane is it has a 90-degree angle in it, a right angle right there.
Yes.
And we're going to we'll put a box on our inclined plane. If you would draw that, please. Then we'll start,
Our box beyond
surprise, surprise, drawing the forces that are at play here. The forces, my inclined plane kind of got chopped off here. Let's get it right. Alright. Are you up with me? Draw the inclined plane on the box on it. Notice it has a right angle. There's no reason why you could not have drawn the inclined plane this direction. The right angle would be on this side. But we had to pick one way or the other, so I picked that. What forces are at play on this box? The one that we always think of first is the weight of the box. Weight is a force. So the thing that's different on the inclined plane is that weight arrow, the weight force, is toward the center of the earth. So here it's sitting on the earth. So the weight is going to come down from the box straight down like that. So notice the inclined plane is in this direction. We're used to studying flat surfaces where weight was perpendicular to the surface like that. So notice it's not perpendicular to the surface anymore. It is at an angle. And so we enter trig land again. So here we are with the weight straight down like that. When we do that, whenever we had vectors that were on a slant, we were always wanting to change them into two components, the vertical and the horizontal. We're going to do that, but the vertical and horizontal are not going to be vertical and horizontal anymore. They are going to be like this. So I'm going to draw in this component, and notice it is no longer a vertical component, but it is perpendicular to the inclined plane. So I'll call this the perpendicular component. Guess what I'm going to call the other one? So instead of having a vertical and horizontal component, I'm going to have a perpendicular component and a parallel component. So the parallel component to the plane is this green one. You can see it's green. This one, and the blue one is the perpendicular component. It still forms a right angle. Alright, let me see if yours turned out to be parallel and perpendicular like mine. Pretty
I
good.
did mine too long.
Good
It's
enough.
alright. Very good. Nice. Alright, you got one component going there. All you need is the other one. Alright, so we have component that's perpendicular to the surface of the inclined plane and the component that's parallel to the surface of the inclined plane. Questions so far? Alright, so this one, the force, I'll just call it the weight. So I'll just put WT there for the strength of that force. The measure of that force is the weight of the box. So I'm going to call this angle theta, so mark it as an angle
Oh, yeah, you can
there.
use
And we will come up, using trig, we'll come up with this side right here. So if I call this side adjacent and call this side opposite, let's actually come up with a trig expression for side adjacent and side opposite. So I know that the sine of angle theta, let's not call it adjacent and opposite, let's call it,
that.
I don't know what to call it. Let's call it the perpendicular component. So I'll put a perpendicular component and parallel component. That's not almost as bad. I want a name for this blue arrow is what I need. So I'm calling it perpendicular component because that's what it is. So if I take the sine of this angle and the cosine of this angle, it's going to help me with that name. So I'm going to do, let's do the cosine first. Cosine is adjacent over hypotenuse. So it's going to be cosine of this angle is the perpendicular component, divided, I'm sorry, it's going to be adjacent over hypotenuse divided by the weight. All right, let's solve that for perpendicular component, because that's what I want. So I multiply both sides by weight, and I get weight cosine theta. So all that, just to tell you that the name of that blue arrow, blue dotted arrow, is weight cosine theta. That's the name of it. What do you think the name of the parallel component is going to be? Well, sine of an angle is opposite, which was the parallel component. Opposite over hypotenuse, which is weight, multiply both sides by weight, and we get the parallel component is weight sine theta. And we've seen this happen over and over, where the side adjacent is connected to cosine and side opposite is connected to sine. So the name of this is weight sine theta. All right. Almost there. Not much theory in this. I guess there's a little bit more. All right. So it turns out we don't really care much about what's going on down here in this problem. What we care about is the force on the box. So do you recall that when we studied forces, I don't know if I still have any of my arrows floating around. Arrows, arrows, arrows. I must have checked them all.
We used them in pre-calc.
Yeah,
We
that's
cut
true.
them and all.
Yeah, we did move them over there. But you'll recall that we can take vectors and move them all around. So I can take a vector that's sitting over here and move it anywhere I want it, as long as I keep the angle and the magnitude true. I'm not going to change it. So I can take this vector and move it up here if I want to, as long as it has the same direction, the same magnitude. So you can probably see where I'm going now. The force down the inclined plane is one of these components. Is it the blue or the green that's going to make this box go down? What do you think, Zach?
The green.
The green. So I'm going to pick the green up and put it where it makes more sense. It can be moved anywhere. So I'm going to move it from here to right there. There is that green component. It's weight sine theta. Right there. That's what's causing the box to go down the plane. Now, from your previous training in my class, what is the force that always opposes motion?
Friction.
Always. We can't ignore it.
Friction.
What is it? Now, normal force is a supportive, is a
Opposed friction.
friction,
Sorry.
force of friction.
Wait.
So, we can't ignore force of friction, so I'm gonna add force of friction to my picture. If the motion is down, force of friction always opposes it. So I'm gonna put in an arrow for force of friction. I don't know how long it is. Hopefully, it's not as long as the weight sine theta, or the box will not go down the plane. But if I want it to go down the plane, hopefully force of friction is going to be less. All right, let's work with force of friction a little bit. And force of friction had a formula. That was a mod ago. Do you remember what the two things were that we multiplied together when we were studying force of friction? Anyone? Videoland, do you remember? What are the
What
two
was that?
things? What are the? Oh,
I didn't sing a yes. I hear a yes
I
somewhere.
heard Emily won. She says that the force of she won too. Emily too. Emily too. I heard her. She said that the force of friction
That
is
is correct.
MS or MK. But since this thing is moving down the plane, I'm going to pick MK. Force friction equals MK times force normal. Does that look familiar?
Mhm.
Yeah.
All right. So.
So,
I'm
we
going
have
to replace force of friction here with MK, mu
So the-
sub K, force normal.
the perpendicular
Okay.
component is the cosine of the
Yeah, the
cosine.
perpendicular is the cosine.
And then the parallel
Throwback
one is
today.
the sine
Uh-huh.
of the weight of theta,
Weight sine theta, yep.
which is the angle.
Between the two, between these two right here, there's theta.
So how did you figure that out? You just chose
It's,
they just made a triangle, chose
Yep.
an angle, and then used.
yep, because we needed to find what was causing this to go down the plane. So we found out from that weight, the component of, we had to create two components, and one of them actually causes the box to go down.
Okay.
It's really quite amazing, right? My wake-up call. If you're asleep, now you're awake. All right,
Oh,
again.
at the same time as